Okay, so we have this air puck of mass 0.25 kilograms. It's tied to a string, and it's revolving in a circle of radius 1 meter. So this circle that's on the table, you know, this puck here is traveling around in a circle. And hey, what's the centripetal force? So chapter 7 is all about centripetal acceleration and centripetal force. Centripetal force is not a new force on our list of forces. You know, the forces that we know, what are the forces that we've been using this year? Gravity, tension, friction, normal force. All of those forces that you learned in chapter 4 can be centripetal forces. The word centripetal just means center seeking. Whenever an object's in a circular path, there's a centripetal force. What is the force that's keeping this puck right here in a circular path? Tension. Without the string, this puck would not be in a circular path. Okay? So let's do free body diagrams. So I'm going to call the puck M1, and then, hey, is this mass underneath the table here? Is that going to be important? Yeah, because look, without this mass under the table, you wouldn't have any tension in the string. If you just had a string going through the hole with no mass hanging from it, there'd be no tension. Okay, so let's do our free body diagrams. FBD. So let's say that here's the puck. Right, so this is M1. Here, let me make that bigger. So M1 is the puck, and then underneath here we have M2, and it's almost like a pulley, you know. You can almost imagine it like a pulley. But anyway, so what are the forces acting on M2? We have M2G down and tension up. Okay, what are the forces on M1? So M1's on the table. So we have M1G down. It's on a surface, right? The M1 is on a table. So there's a normal force. And then tension points to the middle. Then right over here, this is the center of the circle, right? Hey, why is the center of the circle important? Because you always make the center of the circle positive. Why is the center of the circle positive? Because that's where the acceleration points. You want your acceleration to be plus. Okay, so now let's see, what's M2 is equal to what? That guy's 1 kilogram. Okay, and then M1 is equal to 0.25 kilograms. Okay, so this M2G here is going to be 9.8 newtons, right? 1 times 9.8 is 9.8. And then this M1G, that's going to be what? Actually, that's not even going to factor into the problem. M1G is not even going to factor in. This is 2.45 newtons. Okay, so let's sum our forces now. Sum forces. So we're going to do this for M1, and we're going to do this for M2. So summing the forces on M1. In the x direction, what's the only force in the x direction? This way. We only have one force in the x direction. What is it? Tension. So tension equals MA. Now look, this A is a special A. It's centripetal. How do I know that it's a centripetal acceleration? Well, look, where's the center of the circle? The center of the circle is right there. What always points to the center of the circle? The centripetal acceleration. Okay? Now, do we have an equation for centripetal acceleration? We sure do. What can we plug in for centripetal acceleration? V squared over R. So let's just put that in. So this is going to be V squared over R. So that's mv squared over R. All right, in the y direction, so I'm still on M1, we have normal force up and then M1G down. Those are going to cancel to 0, right? Now look, for this problem here, I mean, what I just wrote is helpful and everything, but It's not going to matter. Which actually, I guess that means it's not helpful. What I meant to say was, it's correct. This would be correct, normal force minus m1g equals 0. It's just not going to factor into the solution, though. Okay, so for M2, let's sum forces for M2 now. So what are the forces? So looking at M2 right here, we have tension up and 9.8 newtons down, right? Equals what? 0. It's just hanging there, right? M2 is just hanging there. It's not accelerating. So what must the tension be? When you take this equation right here, you go, okay, taking this bottom equation, tension must be equal to 9.8 newtons. I got to make some room here. So I'm going to get rid of this diagram. We don't really need that anymore. Okay, so tension equals 9.8. I think that's the answer to number 1. What is the tension in the string? Boom, 9.8 newtons. Okay, B. What is the horizontal force acting on the puck? It's the tension, which is equal to 9.8. Right? So basically, we found the tension from M2, which is the same tension as that, because it's the same rope. It's the same piece of string, so the tension's the same. Does this make sense? Okay, third question. What's the speed of the puck? So taking this equation right here, take this, solve it for velocity, which is the speed. Speed and velocity are the same thing pretty much. If you take speed, add a direction, then it's velocity. So basically they're asking for the velocity. So V is going to be square root tension times radius over, hold on a second, over M. Did I do that right? So the tension in the string is 9.8. The radius is 1 meter. They gave that to us right here. The radius is 1 meter. And then which mass is this? The puck or the hanging one? It's the puck. 0.25. And then this gives a velocity of 6.26 meters per second. That's the tangential velocity. All right, then I added a question. What would be the period of the puck? So what do we mean by period? The time for one circle. So for circular motion problems, an equation for tangential velocity. Tangential velocity. The basic definition for velocity is distance over time. So if you focus on one circle, what's the distance around one circle? 2 pi r. What's the time for one circle? The period, which is capital T. So the period, if you rearrange that, is going to be 2 pi r over v. So that's going to be 2 pi, the radius is 1 meter. The velocity, we found it, is 6.26 meter per second. And then that comes out as 1.0 seconds. The period would be 1 second. Okay, any questions on this one? All right, let's try another problem.